So hello everyone, my name is Yishai. I'm a software engineer at Granulate. And Granulate, in short, what we do is we provide companies autonomous continuous workload optimizations, or in other words, we do performance. And today I came here to speak with you about a subject that is very close to our day-to-day job, which is which is how to optimize performance with continuous production profiling. But before we start to talk about profiling, we need to ask ourselves a more basic question, which is, why should we optimize? There are two main reasons for this. The first one is that in most cases in software, faster is just straight up better. The other reason is that if you pay for a cloud provider, like AWS, for example, if you can do the same amount of work with less computing, you can reduce your costs drastically. And generally speaking, your CPU is one of your most valuable resources, and you really want to know what it spends time on. The other day, I saw this blog post in Shopify where they made a study about performance in e-commerce. And they found that 79% of customers dissatisfied with the web performance are less likely to buy again. 64% of smartphone users expect a website to load in 4 seconds or less. 47% of online shoppers expect web pages to load in 2 seconds or less. And moreover, they found that a delay of a single second in load time can result in an 11% loss in in page views and 7% loss in conversions. And I find these statistics pretty impressive, to be honest, and it's a good example of how important performance can be to many services. So it's pretty easy to convince that performance are important, but why profile? And I bet many of you are familiar with the term premature optimization. Google is. And the thing is that attempting to optimize without profiling is pretty much like shooting while blindfolded. Maybe you will find your target, but maybe you won't, and it's definitely going to be a waste of bullets. And you just don't want to waste your bullets. You don't want to waste your precious time attempting to optimize stuff that won't actually benefit the overall performance of your program. So if you are convinced that profiling is important, the next question that you probably ask yourself is, what should I profile and when should I do it? And there is a very simple yet important rule to answer these questions, which is that you want to profile what you want to optimize. Because let's say if you profile your test environment with your test load and test data, you are very likely to find yourself optimizing your tests instead of your actual production environment. And the key to accurate optimizations is profiling the production environment continuously. And let me show a simple example that demonstrates this concept. Let's say that we have this service, and it provides estimations for time delivery of food. Obviously, in different times of the day, the load on this service are different. During lunch, there are many orders. Afterwards, during dinner, there are many orders. And for the sake of the example, let's say that around 3 a.m., people want to have a snack, and in this time of the day, there are more orders as well. So in this pretty dumb example, in different times of the day, the load is different because there are more or less orders, and the data is different as well because in different times of the day, the traffic is not the same, right? So in this kind of service, we need to profile all the time in order to get a complete image of what's going on. And like I said, it's a dumb example, but it actually demonstrates very, very well why it's important to profile continuously, because it's very hard to it's hard to tell ahead of time what our program will act like under different circumstances and different load and data. And profiling is an iterative process. First you profile, afterwards you analyze your results, implement code improvements, and deploy these improvements. And following the rule I mentioned earlier, by which you should optimize, you should profile what you want to optimize. What you want to profile is not yesterday's deployment, but today's deployment. So we want to profile continuously. But of course, profiling production introduces a big challenge. How can we do that without hurting our production environment's performance? Because as most of you probably know, in many cases, profiling has very high costs in terms of performance. So the answer for these problems is what's called samples profiling, or statistical profiling. And the concept is very simple. Each short period of time, we take a snapshot of our program, we take a stack trace. And after we collect enough stack traces, we can actually conclude many things about our program. For example, if we see a certain function at the top of 30% of our stack, we can safely assume that this function consumes 30% of our CPU. So we gather more and more samples, and eventually we will end up with an enormous number of samples, millions of stack traces. So how will we ever be able to produce valuable information out of it, besides things that are very simple? And for this reason, the concept of flame graphs was invented. And flame graphs are merely a visualization for stack traces, and it goes like this. Let's say that we sampled our program and we found this stack trace. We see a function called C that was called by a function named A, named B that was called by a function named A. And the next time we take a stack trace, we see something entirely different. And the next time we see something that is a bit more familiar for us, and so on and so on. And eventually, we'll gather enough stack traces in order for us to feel like they reflect well what our program does. And afterwards, we'll be able to sort them and remove these boxes. And this is flame graph. And when we look at our stack traces like this, we can actually tell many things about them. We can know many things about our program. For example, in this made-up program, I would say that function C looks interesting because it has relatively large amount of total time, which refers to the total time in which our process was executing the code in this function. And moreover, it has relatively lots of own time, which means that in many stack traces, this function C was at the top of the stack, which means that this function is the one that actually used CPU. So now let's move on to a simple example written in Python. We have these three functions. The first one sums up the first 10 million numbers. The next one sums up the first 100 million numbers. And the third function sleeps. Our main function is very simple. It only calls these three functions one after the other. And now let's pause for a second and we'll try to guess how the flame graph of this program would look like. So regarding the sum functions, it's pretty easy, right? We know that we expect to see much of the flame graph is taken by the sum 100 million function. About 1/10 of this amount will be taken by the sum 10 million function. But what about the third function? What about the sleeping function? And this leads us to an important concept regarding flame graphs, which is what we want to look for when we searching through flame graphs is for CPU consumption. And when a function performs sleep, when a process runs this function, it does not consume CPU, and therefore we don't care about it, and we wouldn't want to see it in our flame graph. If it does not consume CPU, we won't see it if our profiler do what it should do. And indeed, we will use a PySpy, which is a Python profiler, to profile this function, and this is what we get. We get the module has its own code which is being executed, so we will see it in our flame graph. We see the main function, and the main function calls sum 100 million, and right there at the bottom right, you can see this pink rectangle representing the sum 10 million, and indeed we don't see the sleep function at all. So now that we are familiar with the concept of flame graphs, I will be able to show you some more advanced examples. For these examples, I will use Granulate's continuous production profiler, which is called gProfiler. But these same concepts can be applied to any other profiler that can give the same kind of data. And let's move to a live demo, and hopefully everything will behave correctly. Okay. So this is our program. Can you see it? No. It looks. Is it clear? Can you see it well? Okay. Oh. So what do we have here? Where I went to SQLite tutorial to take an example DB, and in this DB in this DB we have names of artists and songs and other kind of information related to music, and what I wanted to do is to build a simple Flask application that will allow us to check whether certain artists are in the DB. And as you can see, this is the entry point for this query. And in this function, most of the job is actually being done. And since I don't know anything about SQL Alchemy or SQLite in general, what I did to get this code was to search in Google and copy the first answer in Stack Overflow that I found, and that's probably what any programmer would rightfully do. Do you see any problem with this function? Do you have any idea what might be wrong with it? So yeah, I didn't have either, but exactly for this reason, we have flame graphs. And so I ran this program, and I took and I profiled it, and this is what I get. In gProfiler, we can filter by containers, so we will see only this application and not the other application that I used to. Not the other application I used. I used to provide traffic, and it doesn't work. Just a second. Okay. So as you can see, there are many stuff going on in this flame graph. Most of it is Gunicorn, which I use to execute the program. But this is the relevant part. And this is the part where our function is at, as you can see, check artist. And as we expect, this is the does artist exist is most of the work that our main function does. And conceptually, when we look at this function at the flame graph, and this function is called that does artist exist, we know that what we expect to see is a call for the DB. And indeed, this function, this query.scalar, is actually the one that performs this query to the DB itself. And indeed, it takes most of the flame graph under this function. But we also see other functions as well that we wouldn't actually expect to see there. We see this exists function, which we are not familiar with, and this equal function, and in Python it means that there's some usage of the equal sign, which is translated to a call to this function. And indeed, when we go back to our function, we see what we saw in the flame graph. We see this query function, and afterwards we see this scalar function. That, as I said, these are the functions that perform the actual query. But in here we see this function, and we are not completely sure that this function actually needs to be there and be called each time we call the function. And at first glance, it doesn't seem like much, but after we see these function calls in the flame graph, we actually know that they consume a relatively large amount of CPU. And now that we know that these functions might be interesting, we can look at the SQL Alchemy documentation and see that these functions provides the SQL query that will be used, and they indeed don't need to be called each time. And this is the fixed version, where the does artist exist looks exactly the same. Besides that, in the query function, there's a call to another function on which I used the Python cache function. And therefore, if I call this function with the same name of an artist twice, only it will generate the query entity only once, and afterwards it will continue to give me the same object. And when I execute it, it will look like this, because eventually what we care about is not what it looks like in the flame graph, but we actually want to see that there is some improvement. So let's start with running the bad version. And as you can see, there's no magic here. It's just a call to the container that contains the application. And we can execute it. And we'll execute another script that will provide some traffic. And we can use Docker stats to see that this container consumes around 55% CPU. Sometimes it's more, sometimes it's less, but it's around 55%. And indeed, when I actually, let me show you how the execution of gProfiler looks like. It's just a single line of a bash that performs all the magic. So it's very simple. So this is what we have. And now I will run the other one, the fixed version of our program. And this is what we get. As you can see, it decreased from 55% to 50% or less. So we know for a fact that we actually managed to improve our program in more than 10%, and we did it pretty easily. So this so as I said, this function, this program is very simple, but in real life you will see examples that are very similar to this, that someone, as I said, rightfully so, took some code that from Stack Overflow, and he didn't think about all kinds of performance implications, and this is what he ended up with. And using flame graphs, it's very visible to see the problem in this program. By the way, after we deploy, we can take a look at the fixed version, and this time around, you can see that I'm looking for the function. There it is. You can see that the frame is actually smaller, and moreover, you can see that it actually only calls what we expected it to call, which is the query itself, as you can see here. So this is our first example. Our next example will be of a real-life scenario. I'll try to, oh, okay, we're here. So this is a flame graph of one of our servers, applying the concepts that I talked about earlier. We do use gProfiler regularly on our services, and this is the flame graph of one of our servers, and highlighted you can see the remove handler ref function of the logging built-in library of Python. And it doesn't look like much, but these kind of functions, even though it's only 3%, it adds up. And when we looked into this function, this is what we saw. And like in like in the previous example, at first glance, there's nothing wrong with this function. Does anyone have an idea what might be wrong? This one is very, very simple Python function. All of what it does is it acquires some lock, checks if some element is in some list, and if it is, it removes it from the list. And this code is not very problematic, but if your list is very, very long, like we did like it was on our server, in this code actually traversed through the list twice. First time in the if, and afterwards in order to remove the element. So we actually proposed this fix to the Python community, and it was got upstream for 3.10, I believe. And these two implementations, the first one checking if the element is in the list before removing it, and the other one just attempting to remove it and catch the exception, these two implementations are exactly the same in Python, but the first one was twice as harmful for performance. So by profiling and finding bottlenecks, you can actually benefit the open source community as well. Originally, I wanted to show some advanced techniques, but unfortunately, I will not have the time for it. So that's it. So I really hope that that now, after you heard this talk, you will feel more comfortable using profilers in your production environments, and I'm absolutely sure that you will find many bottlenecks that you did not expect to find. So that's it.